Okay, welcome everyone to the combinatorics seminar of this week. This is a pre-seminar. This week, we're very happy to have our own Catherine Babecki, and she's going to talk about error correcting codes for the pre-seminar. And feel free to unmute yourself at any time if you have any questions. Take it away.
Yes, please do ask questions as you think of them. We definitely have time for it, I believe. So I'd rather you come away understanding some things than I blaze through everything and then you're like, wait, what happened? So today, as Lei said, I'm talking about error correcting codes, which I have illustrated here on the title slide. So the idea is that you're sending information through a noisy channel in a string of ones and zeros, like you've entered the matrix kind of a thing. But what I mean by noisy is that there's a possibility some of these ones and zeros might be getting flipped just from like random noise happening. So we want to be able to transmit this information efficiently, but without being susceptible to these errors. And that's where the idea of error correcting codes come in. Let's see, yes, so we're going to focus on binary codes today, but you could consider codes over a larger alphabet than just 0 and 1. So for instance, if you had zeros, ones, and twos, that would be called a ternary code. Obviously you can generalize, but we'll stick with zeros and ones for now. So we're going to be considering strings of zeros and ones of length n. And all of those possible strings are called the set of all words. And a binary code is just a subset of all of the possible 0 to 1, 0, 1, and length vectors. And if we have an element in that special subset we're calling our code, we call that a code word. So we would like to pick this special subset C, our code, so that it, as I said on the title slide, is as expressive as possible, but we're still robust to errors. So even if we have some noise in our channel, we can still recover what message was trying to be sent. So let's look at a really simple example. Suppose we just have one bit that we want to transmit, either a 0 or a 1. Take your pick, whichever one you like better. You can pretend that's what we're sending. So one of the simplest codes you can construct is the repetition code, where instead of sending just a single 0 or a single 1, you can send that bit multiple times. I chose 3. Odd numbers are typically a little better for doing this. In that case, there's sort of no ambiguity over what you should decode. But there's nothing special about 3. You could do any number you wanted, but we'll stick with 3. So what we do is we take our message, we triple it, so 1 0 becomes 3 zeros. We send that code word through our noisy channel. Possibly something goes wrong in transmission. So say instead of receiving that 0 0 0, we sent some stuff happened beyond our control and we accidentally received 0 0 1 instead. Well, we know the message had to be either a 0 or a 1 because we've designated that our code words are only the possibilities that we've just got this triple. So it would make sense to choose to decode this received message by picking the all zeros or all ones vector, depending on which is closest, like which matches up on the most digits. So if we receive 0 0 1, we would decode that as 0 0 0 because we were only off by 1 bit, which means our initial message should have been just a 0. And so we've done not only this error detection, so we've noticed that something wrong happened when we sent our message, but we were also able to recover the message that we initially sent, which is called error correction. So that's where the error correcting codes go in. You want to know not just when an error has occurred, but can we fix it? So there's some problems with this code. It's not very efficient, especially if you were going to repeat your code word a lot of times. You know, maybe you chose 7 instead of 3. It's not very efficient. So you're taking then 3 bits or 7 bits or however many bits you want, to transmit only 1 bit worth of information. Not very speedy. However, so inefficient we can deal with. We're going to talk about some more efficient codes in a second. But an unavoidable error that we won't be able to get away from is that if many errors occur, we might not be decoding the right message. So for instance, if we had taken our message 0, turned it into our code word 000, and our noisy channel was so noisy that we got back 101, we would then decode that. So, oh, our code word must have been 111, and that means our message would have been 1. So it's not a perfect system, but you kind of assume that your channel isn't too noisy. So the odds of 2 errors occurring is like way worse than the odds of 1 error occurring. So that's typically the sort of framework we'll work in, that errors are rare enough that usually the word that is closest to the word received is actually what we were looking for. Cool. Before I move on, any questions here about repetition code and sort of what we're trying to do with these codes? So we need some words to describe our codes. So N is the length of the code. That's how many zeros and ones are in a code word. So for instance, our repetition code had length 3 because we were taking 3 bits to transmit all those words. The rate sort of tells you how much information are you sending over how many bits do you need to do it. So it's like a measure of efficiency. With the repetition code, it took us, we were only sending 1 bit of information and it took us 3 bits to do that. So its rate is 1/3. You would like the rate to be as large as possible. That would be a more efficient code. And the distance of a code is the minimum Hamming distance between 2 distinct code words in the code. And the Hamming distance, I've sort of referred to it not by name already, but it's the number of coordinates that 2 code words or any words differ on. So for instance, the Hamming distance between 001 and 000 is 1 because they only differ on 1 coordinate. However, the Hamming distance between 000 and 111 is 3 because they differ on all 3 coordinates. Cool, so that's where we were. We've got length, rate, distance, and just for completion, the distance of the repetition code is 3 because the only 2 code words in that code are all zeros and all ones. And as I just mentioned, since those ones differ on every coordinate, we say they have distance 3. So more formally, the way I said earlier that we're looking to sort of maximize efficiency while remaining robust to errors is we're looking for codes that both have a high rate and a high distance because the more distance between code words, the more robust to errors you will be. So we need to look beyond the repetition code for good codes because they're never going to be very efficient. The rate is always going to be low. And one place to look is using some linear algebra tools. So a linear code is just a linear subspace of 0, 1 vectors of length n, where we're thinking of this as a vector space over the field of 2 elements, 0 and 1. So we've got binary addition happening, 1 + 1 = 0. And so one way to describe a linear code is by a parity check matrix, which is just saying there is some matrix out there so that our code is the kernel of that matrix. So for our repetition code, this is the check matrix. You will see if you do some algebra out that 111 and 000 are the only vectors such that this times that equals 0. Cool. There are other ways to describe linear codes. For instance, there's a thing called a generator matrix, where your code is the row span of that matrix, but I'm not gonna talk about that one. It's less important for our purposes. And the Hamming code is a very special linear code. So that's where we're going to focus the rest of our energy. So for every integer greater than or equal to 2, we can define a Hamming code, which I'm going to denote HN. I don't know if that's terribly standard, but that's what I'm going to call it. So the Hamming code HN has length 2 to the n minus 1, and its check matrix, which I'm calling MN. The columns of that matrix are the numbers 1 through 2 to the n minus 1 written out in binary. And this Hamming code always has rate 2 to the n minus 1 divided by 2 to the n minus 1. And they're always distance 3, no matter how big n is, or what n is. So you'll notice as n gets really big, this gets pretty close to 1, and that's good on efficiency terms. So let's talk a little bit more about this binary stuff. So here is the check matrix for the Hamming code H3. We see we've got a 7 by 3 matrix. And these columns are the numbers 1 through 7 written out in binary expansion. So the first row is indicating, is there a 1, is there a 2, and then is there a 2, is there a 4? So this column is 1, this column is 2, this column is 3, because we have 1 plus 2, 4, 5, 6, 7. And the columns corresponding to the powers of 2 are called parity bits, and all of the other columns represent data bits, which I've color-coded here for you guys. And what that means, sort of, so before how, like with the rate, how it's how much information are we sending over, how many bits do we need? So the data bits are the bits that are like carrying our information, and the parity bits are what are allowing us to correct and detect errors. So how do we take these magical 4 bits of data and turn them into a code word? Well, that parity check matrix gives us a set of linear equations. We know our code words have to be in the kernel of that matrix. So if we write it out, that means, the first row gives us this equation, the second row and the third row give us the rest. So if we take some piece of data, say we want to transmit 1011, we sort of stick that in our data bits places, and then we use these equations to solve for the missing parity bits. So we can do out that addition, just rearranging terms and then plugging in the numbers we know. We can solve for what x1, x2, and x4 have to be if this is going to be a word in our code. And you'll notice the way I've written these equations, we can see that each parity bit is uniquely determined by the data bits. So there's no ambiguity going over here. A data bit could not correspond to 2 code words, for instance. And every bit of data we wanted to send, or I guess every chunk of data we wanted to send, not to confuse my math words and my English words, we can represent as some code word. Cool. So if this was what we wanted to transmit, this would be the message we send. And let's then see how that works. So we've taken that message, for instance, this message, we send it through our noisy channel. And what happens on the other end is that someone receives the message we intended, possibly plus some little error term that we would like to be able to get rid of. We only know what Y is. We would like to figure out what our message was. And there's a very nice way to decode a Hamming code, or really any linear code, but Hamming codes are extra nice. I'll talk about why. So the syndrome of a message received is you multiply that vector by the matrix. And since our code words are chosen to be in the kernel of that matrix, this is the same thing as if we had taken the matrix times the error that happened. So this syndrome is telling us the sum of all the columns where errors occurred. Let's see how that works with an example. So suppose we received this message and we were using the Ham encode H3 that we've been talking about for now. So that means the syndrome of this message, we can compute that by doing this multiplication. It ends up being 101. So we look at, ignore this for right now. We look at 101. We're gonna sort of take on faith that errors aren't too likely. So instead of looking for, some sum of columns where errors have occurred, we say, can we find a column that matches this syndrome? And with the Ham encode, yes, there is. Since we've got all of the numbers we desire written out in binary, every possible column of 0 and 1 vectors appears exactly once in this check matrix. So no matter what syndrome we get, we will uniquely find a column in our matrix, which then tells us what bit has been hit by the error. In this case, so 101 is the 5th column. So that means our 5th bit is wrong, which means our actual message we wanted to know, we just have to flip that 5th bit from the message we received. And that means this is what we wanted to send. So that is how you send and encode and decode the Ham encode. And this went a little faster than I was planning. So that was actually all of the slides I have. But I'm happy to answer more questions if you guys have any, because there's plenty more to talk about. This just went a little quicker than I was thinking. No one had any questions. I was expecting questions in the middle.
Can I ask something?
Yeah.
All right. So going back to the fact that you took that leap of faith of there being, can we go one slide back?
Mm-hmm.
That leap of faith of like the error, the ME error is it like, what am I trying to say? You're taking this leap of faith that there's not that many errors. Is there a way to maybe account for there being like 2 errors in a very long message?
Yeah, so actually with the Ham encode in particular, is the annotate feature working on this? I don't know if there is. Okay, I don't think I can draw on the screen, but I can wave the little mouse around.
Okay, okay.
So there's a thing called, for the Ham encode in specific, you can put an additional parity check where it sort of, I think you have to stick 1 extra column here, and then you stick a row of all ones at the top of that. And the linear code that gives you, so now you need 8 bits of data to transmit messages. But this code can not only correct and detect when you've got a 1-bit error, it can also detect when you have 2 bits that have gone wrong. But it can't correct the 2 bits. It only tells you that something is off. It doesn't know how to fix the problem. Yeah, so there are definitely ways to get fancier. But for this one, this is a sort of like a bread and butter error correcting code, one of the famous ones.
That's good. I do like bread and butter.
Yeah. Oh, this is still just so nice.
Yeah, it's like very pretty.
Yeah.
Have you looked at BCH codes, for example, where you can correct more errors?
I haven't gotten to them yet. I've read some about how-to-mard codes, and I think Reed-Solomon is on my list at some point, possibly. I think I'm under the impression that Reed-Solomon codes are kind of like the Ham encode, but instead of, there's some like polynomial stuff going on. But yeah. There's lots of codes for me to look into for future work.
So I've done a little bit of work with this, but when I was doing this, I mostly viewed all of these things as polynomials in F2X. So is there a way to view the encoding and decoding in terms of polynomials?
Almost certainly. That isn't the framework I've learned much about yet. But yeah, I think all of this stuff starts getting very like finite fields, polynomials very quickly.
Any other questions?
I was going to ask,
Go ahead.
can you explain Hamming distance again? Because I think
Oh,
I
yeah.
misinterpreted. I think I was thinking of like between two given codes, you measure the Hamming distance, but then
No, so it's so the Hamming distance is defined on the words, so just the strings themselves. So for instance, this vector and this vector have a Hamming distance 1 because they differ on exactly one coordinate. Same with these guys, they differ on one coordinate. Same with these guys, they differ on one coordinate. But if we look diagonally, this one and this one have a Hamming distance of 2 because they disagree on these two. So if you want to think about Hamming distance for other finite fields, it still is just how many coordinates do they disagree on. There's nothing changed about that. So, like something, if you've got like 7 elements or something, it doesn't matter if the elements are like closer to each other in some other sense. As long as they're not the same, they're different. Exactly the same amount of different, if that makes any sense. And then the distance of a code is the minimum distance between any two vectors in that code. And if it's a linear code, actually this distance is exactly the same as the weight of a minimal code word, where weight is just you count up how many ones are in it.
That's nice.
Yeah, it is really nice.
So are rate and distance kind of like at odds with each other a little bit? Okay.
Yeah, so it's sort of a balancing act. How do I get a code that's both distant and effective, really high rate? And as n gets really big, the rate of the Hamming code gets really good. I think I mentioned that briefly. Yeah, so this approaches 1, which is very nice. Although the distance never changes, but yeah, whatever. Distance of the repetition code is 3. So the only 2 code words in the repetition code are these 2. Every other string of 301 bits is not a code word. So we only have two words to look at, and their distance is 3 because they disagree everywhere. So the minimum distance between 2 code words is the distance between the only 2 code words they are, which is 3.
Can I ask one more thing?
Of course.
So if we go back to the definition of rate over in like some other slide, I forgot. So are we? Is rate just supposed to mean how many message we could send in the whole big space? Because I'm like, if we got rid of that log and put a 2 to the end of the bottom,
yeah,
right? Like, so it's kind of like measuring how many. Is it just measuring how many messages are available at our disposal?
Sort of.
That are
So
valid?
what you said is exactly that. If this just said size of C over 2 to the n, that would be how many of the total words out there are in our code. Like, what proportion is that? But I think the way that I think about rate the best is that it tells us how many bits do we need? Like, what is the ratio of bits of message, like bits of information being sent over how many like bits being transmitted total? So for instance, this Hamming code has rate 4/7 because it takes us 7 bits total to transmit 4 bits of information.
Thanks.
In the chat, I don't actually know what the taxi cab metric is, but hopefully it is indeed similar.
I have a question about the errors. So is it normal to like say try to assign a probability to some error occurring? And
Yes.
then like okay.
Yeah, there's a usually or like there's a lot of instances where you are like you know what the probability of an error occurring is. And usually it's pretty small, for most cases. Although a fun fact is that it is equivalent to think, or like, if the error is really high, like if, that's just as good as if the error was really low. So if you knew that the probability of error was like 0.99, it's just as good as if the error was like, 0.01 or whatever, because you just know that every bit is going to be flipped probably, which is the same as if it had sent correctly. So the real problem is when the probability of error is near a half, then there's no hope of decoding because everything is just kind of random junk. Any other questions? This has been good. You guys have great questions. Yeah, I think there's a lot of cases where most of the time you're expecting that your channel is, something about it. So the probability is known and not changing. Or if it is changing, maybe you know something about it, like the space weather is weird today. So all of the zeros and ones being beamed down for our satellite get a little weirder, when the full moon is out or something.
Is there like so like in the definition of this parity check matrix, it's like some matrix with prescribed kernel.
Yeah.
Is there like an industry of like changing that matrix, or does that not really affect the story?
Yeah, so there's quite a few of the like taking codes and making new other codes with different properties operations depend on these parity check matrices or generator matrices, which I haven't talked about. For instance, you can like concatenate them, and there's some theorems about what properties carry over in what way. And for instance, if you can like take out a column of something and that does something, or stick some extra ones at the top and that gives you another bit of error correcting. Yeah, there's all kinds of fun ways to tweak the matrices and get fun things that do new stuff.
The dream is to get fun things that do new stuff.
So actually there's a funny story which I will retell briefly in the main talk, but one of the constructions I use for my nice results came because I misread what was meant by one of these matrix like changing operations. I thought they were saying there's something called a punctured Hamming code, which is where you take this generator matrix I haven't told you about and drop a column from it. And I thought they said drop a column from the parity check matrix, which I think is not anything anyone cares about. But it worked out very well for what I was doing. So it's good to misread your textbook sometimes.
Yeah. Rad.
So this thing of looking at columns of matrices, that reminds me of matroids. Do you know if there are any connections with those?
Probably somewhere. I don't know any specific ones, but it seems very believable. Oh, and another fun, also matroid seeming fact is that the distance of a code is also the maximal number of linearly independent columns, I believe. Or like, yeah, like how many columns can you pick if you picked any number of columns from all of these columns, would they be independent? Or something like that. No, that's not quite right. It's a minimal number so that you're always dependent. That was close. Any 3 columns you pick, something like that. Something like that. It's in there somewhere. I don't remember. I wasn't
If
prepared.
you stare at the columns long enough, you will see the distance.
If you just start adding things, maybe it'll work one day.
Okay,
Yeah.
let's all thank our speaker first. Feel free to unmute yourself.
Woo!
Hey, thanks for coming, everyone. What a great crowd.
Yeah, now we're gonna have a 10-minute break.
Yeah.
Really nice pre-seminar.
Yay.
I really enjoyed your slides. They're
Thank
very
you.
visually captivating and I understood them all. So
Good.
thank you.